Hi, I'm Madhu. I've worked at Altiux. We are a product engineering services company, especially catering to the IoT side of things. We have expertise in the embedded space, and we develop solutions for customers like the servo motors, the sensors, actuators, and the gateways, and on the cloud side, end-to-end IoT solutions. So we're headquartered in Bangalore, India. Most of our engineering staff is in India, and we have a presence in the US in Dallas. Mark is our senior director of sales. He's trying to drum up business for us in oil and gas and in the Dallas area. I work out of Silicon Valley, Mountain View. I head the engineering team there, and the current customers that we have. Yeah. So, as I was sort of trying to prepare for this conversation, we wanted to showcase the software side of the IoT. Ed and Particle.io, Edge Tensor, they've showed basically a lot of vertical solutions and wireless technologies and as such. But we wanted to sort of try and show you what it takes to actually develop an end-to-end solution for most of these technologies. So I copied Ed's introduction to IoT and how he thinks about IoT, because I thought it was, it puts into perspective what we're trying to do. So it says IoT and MPM gives you the ability to remotely monitor and potentially control devices and objects in field. It's pretty much a very simple problem, but there's a lot of complexity involved, and there's a lot of software pieces and multiple companies coming together to get a single ecosystem, right? So the way, at least I think about it, IoT is in 4 stages. On the endpoint side, it's mostly the sensors and the actuators, which are trying to do something. They're a single point of focus. They don't have much compute. And then there is the gateway, which is the communication aggregator, which is trying to aggregate the communication. IoT fog and IoT cloud are sort of a little, I sort of lump them together because they are scalable compute. There's no limitations there. There's some limitation on the IoT fog, and on-premise orchestration is one thing that that's gonna probably help us there. But IoT fog is mostly just to ensure that we, at least from an IoT standpoint, that the latencies are more contained than actually going to cloud. So some parts of the cloud applications transfer to the IoT fog side. So with that, a quick introduction about us. So we are a product engineering services company. That means that we basically help OEMs, ODMs, typically of instrument manufacturers, or even wireless manufacturers to sort of develop an end-to-end solution. So we offer engineering services from both the software side and the hardware side. Typically on the hardware side, we are just an integration company. We're not like really designing chips or anything, but get everything out there or design a solution for you based on whatever is available. Most of the time, our focus vertical has been smart infrastructure, industrial IoT, and smart buildings. That's been that's where we see most of our customer growth happening. We typically are not dealing with the consumer side of IoT, which is what the Googles and the Amazons of the world are doing. We belong to a few associations, and most of you would probably are familiar with them. The Thread Group, Bison Alliance, and the like. So these are again just our services that we offer. So we offer even consulting services where a lot of times what we see is that customers have an idea and they want to take it to the market, but they're like really in the initial stages of their journey. They don't have a clear business model yet, so they would like to spend some, trying to understand this field. So we offer consulting services as well, and then of course software development services, system integration, and then maintenance. Okay. So what I wanted to talk about in this talk is the building blocks of IoT as far as how we see it from a software standpoint. We've all discussed a lot about the technologies in place, especially the wireless networks, etc. But I just wanted to sort of go through what it takes to actually build an IoT solution. So I'll start from the left side of the screen. Can you see? Sorry, I just want to see if you had a problem with that.
Yeah, we couldn't make out the third item with the cloud above it.
IoT fog. Yeah.
Oh,
If it's too small, let me just repeat some of these things. I think the fonts are a little smaller. So on the left side are IoT endpoints, and these are some of the characteristics of the IoT endpoints, right? So typically they are single function. Whether they are low compute or not is it's debatable, because some of the industrial machineries, they're not low compute, they have a lot of compute, but they're typically single function. And they do one thing, and that's what they're doing. And they have and usually in the wireless space, for smart lighting or smart infrastructure, it is an MCU class device. It's a pretty low powered, in some cases battery powered devices. So the main point is that it is a very constrained environment, and there are specific software stacks that are available for them. There's single communication. That means, again, usually one type of communication is coming out of them. It could be wired, it could be wireless, but their whole point is to just send some data and accept some data back. Typically mesh and wireless networks. We saw a presentation from Particle.io. We saw Ed's talk about the different wide area networks, low power wide area networks. So those are the type of networks that are there. Legacy connectivity, what we call legacy connectivity, is basically just Modbus or Ethernet type of connectivities for the devices in the buildings and in the rest. Now moving on to the side is the IoT edge gateway. The edge gateways are a step higher in computation power. They are like the Wi-Fi routers in the world. Actually, one of our customers brought up a great analogy. He talked about your personal wearables, like your watch and Fitbits and the likes, and your cell phone as the next level of compute. So your Fitbit is actually talking to the cell phone, and then the cell phone is actually talking to the cloud. So that's pretty much the three-stage architecture, even in IoT. So you have sensors which do one or two things well. You have the gateways, which are like aggregation, like similar to a cell phone, but there are of course a lot of differences. But so they are responsible for connecting the sensors, managing the sensors, and then taking whatever the sensor data is back to the cloud, and also taking whatever management that is coming from the cloud back to the sensors. So they are higher power devices, typically a microprocessor-based system. Most of the times their work is to sort of do a communication convergence. What I call north and south and east-west communications. So north and south is basically taking data from the sensors back to the cloud, and from the cloud back to the sensors. And then east and west is sometimes sometimes you need communication from different sensors back into the sensor. So basically, let's assume there are a couple of sensors which are talking two different communication mechanisms, but they're connected to one gateway. So without actually going back to the cloud, they can talk through the gateway to each other. Again, those are more resilience operations. One example that I can probably give you is like a smart home. One of the customers that we are working with is a building management company, and they want to manage their apartment infrastructures through a gateway, similar to how a Google Hub or Amazon Echo is going to manage your lights and stuff like that. So, but they're looking at it from from a building management perspective, not from a consumer perspective. So now they have sensors that use different wireless networks, either Zigbee, Z-Wave, Bluetooth, and then they need a gateway which sort of helps communicate between the sensors. So they can actually send a communication from one sensor to the other sensor. Let's say that a leak sensor needs to switch off a valve. So without actually going to the cloud, they need to send a message. As soon as a message comes from the flooding sensor, the valve is turned off by the gateway. So that's the east-west type of communications that I want to know. And more and more, we are also seeing edge analytics coming to the gateway, and in fact coming to the sensor nodes as well. Edge tensor is a good example of that. We have a customer who's working on a neural network chip, a very low power chip. In fact, it's actually going into the IoT endpoints, not necessarily on the edge. So that's another area that is comes under this IoT edge capability. From a fog perspective, again, it's just a next level of computation. It offers a little bit more scale, actually a lot more scale in terms of computation when compared to the IoT edge gateways. We see the following as their functions, but there are many. So multi-cloud integration, where we think we'll talk about this a little bit. Protocol translations and messaging and routing, data ingestion, and again edge analytics or filtering of data based on some criteria, so that you don't fill the bandwidth to the cloud. Cloud, I think everybody is familiar. Almost infinite compute, data analytics, as well as applications, user applications. So, using the same diagram, these are some of the software components that we typically deal with within each of these IoT endpoints. For IoT endpoints, most of the time it's a micro OS, it's a bare metal OS or some kind of an RTOS that we're working with not a lot of system capabilities that are available. There are actual software drivers that are driving the sensors and networking stacks, security of course, and then there's some component of a user application which is managing the sensor, either collecting its data or telling the sensor what to do. And then there is of course management of the device itself, security patches, over-the-air updates, and configuration based on different scenarios. The IoT edge, most of the time, it's a mix, but typically what we see are Linux-based systems, similar to a Linux server, but the class of compute is much lesser than a full-blown Linux server. And then there are multiple communication drivers as far as the communications go. The Ethernet, Wi-Fi, low power wide area, wireless communications, and then multi-cloud integration is something that we'll talk about, but just cloud integration in general, just the data going back and forth from the cloud. Edge analytics we already talked about. In terms of IoT fog, it's again multi-cloud integration, protocol translations. On IoT cloud containers and cloud orchestration. To your point, that's probably also coming to the fog, and we see some of that coming to the edge, IoT edge as well. And then of course user applications. So this is a type of software stack. It's just a sample software stack. It's it's pretty generic. This is something that I just wanted to sort of show and see what are the types of software that is available on an end node. So you have a hardware layer, which is over a serial interface, or some kind of a GPIO interface, which is actually talking to the sensors, which is actually talking to the communication drivers. You have OSs, typically quantity TinyOS, FreeRTOS, or sometimes just bare metal, just a scheduler running, and then you want to run something. On the Mac and Phi layers are the the first layer of communication from the wireless and internet standpoint. So typically there's LoRa, 802.15.4 Max, which is basically a host of protocols, Wi-Fi, 6LoWPAN, IPv6, and Thread. They all use 802.15.4. BLE, which is Bluetooth. And then you have the transport layer and the transaction layer, which is a USB tiny PwR. Then the next level of the data is basically just managing the network, managing the device itself. So you have some kind of an encoding, which is JSON or XML. XML is too heavy for a small device, but is that?
It's almost always JSON.
Yeah, it's always. Now, I mean, everybody has sort of moved on to JSON. There's, XML is pretty much not existing, but there are some, legacy systems which still operate on an XML basis. So, and then there are open standards. For example, lightweight M2M is a standard which defines like objects for configuration. So there are standard objects that are defined by standards group. So they allow us to sort of do some of the common configuration tasks. And most of the time the configuration task is setting up the wireless parameters for a particular environment, commissioning keys, doing firmware updates on the device, and the like. So moving up to the software for gateways, right? So as you can see, the complexity has sort of started going up because there is a lot more that a gateway does. Whenever I sort of try to explain this, I think about a normal Windows or a Mac OS type of system, right? The amount of configuration or amount of device management that these systems offer is something that we just take it for granted. For example, firmware updates, security patches, everything is working fine. The applications are managed properly. If something goes wrong, they are killed automatically. But none of those sort of exist out of the box in the IoT edge thing. And most of the times, a lot of companies spend a lot of time trying to do the same thing over and over again for different IoT gateways. And that's the area where we feel that there is a need for some of our frameworks to sort of reduce the time for development. And we'll talk about the frameworks a little bit more. But just to give you some idea, so again, this is the physical layer where you actually have the communications devices. You have the OS layer. Typically it's Linux, OnTiki, VxWorks, they have their place. But most of the time what we see is that these are Linux-based systems. From a communication standpoint, you have cellular or Wi-Fi Ethernet, which is going to the cloud side, which is the larger pipe, so to speak, for the data part. And on the south side, which is actually connecting to the sensors, you have the 802.15.4. It's a sub-gigahertz channel, and the advantage is, of course, low power and larger distance. And then there's BLE and the likes. The network layer, IPv4, TCP, UDP, pretty standard. From our transaction layer, again, we are talking about a lot of standards-based protocols like PwR. PwR is like a tiny HTTP REST protocol. It mirrors a lot of concepts from HTTP and HTTPS, but it's meant for devices which are constrained, which really are not transmitting that much amount of data, but they have, they still need similar concepts to go talk to servers and then come back again. Message encoding, again, management layer, the same concepts that we saw on the end devices, but they are more comprehensive for the IoT gateways, because not only is the IoT gateway managing the end device itself, it has to manage itself. So if you imagine, it will be like an end gateway managing a fleet of sensors, and in an end-to-end application, the cloud application managing a fleet of IoT gateways, and then the fleet of sensors. So, one typical example would be that you would have a gateway for every 200 or 300 streetlights, and the streetlight would have a wireless, low-power wireless communication sensor to switch it on, switch it off, do whatever we want to do it, and get the data. And then there would be a gateway sitting, perhaps for every 100 or 200 streetlights, in some cases, thousands of streetlights, and then, controlling those streetlights from it. So if I need to do a firmware update on those streetlights, what would happen is that the gateway is responsible for it. It's not that the firmware is coming all the way from the cloud. So the gateway is like your local proxy server, and then it is responsible for ensuring the health of all the sensors. It's responsible for ensuring that there's communication going back and forth. Okay, so this is can you guys see it at all?
I don't know. Larger screen.
Can we get a copy?
I mean, the video was, when I look at all the videos on YouTube, I imagined a lot bigger screen. So sorry for that. But I'll try my best to sort of just walk you through what we do. Based on some of the information that some of the problems that we saw, like device management and all of that, right? What we felt, and having worked with about 40 plus customers, what we felt is that we keep seeing the same problems over and over again for different people. So we've developed frameworks around to address, first of all, from an engineering perspective for ourselves, just to make our life easier. And then we started seeing some patterns there where we thought that we needed some common frameworks. So we sort of labeled the collection of frameworks to be BoxPwR, because we are powering boxes essentially. What it helps us do is, when customers approach us, it helps us sort of get them to the market faster, because we're not repeating the same thing over and over again. And then we have a set of tested components that we can reuse across different solutions. And I have a few use cases after the tech part of the talk, and perhaps it becomes a little bit easier. So anyway, just to quickly walk you through it, we have a bunch of frameworks here. And I'll just explain at a high level what each framework does and why we need those frameworks essentially. So at the bottom layer, it's core framework. I'm sorry you guys can't really see it. It's basically one example of a core framework is what we call as the radio adaptation layer. So what we see typically is that when somebody is developing, let's say one of our customers was developing a vibration sensor for robotic arms in factories. So they would put the vibration sensor on a robotic arm, and then of course measure the vibration, and depending on the collected data, figure out if there was a problem on the robotic arm or it was going out of some variance essentially. When they approached factories to sell to, they had different conditions. First, they started with sub-gigahertz wireless, which is low powered, but they had some issues with the hardware. Then they went to Wi-Fi, but in some factories there are actually shields on the robotic arms, so the Wi-Fi is completely blocked. They cannot use Wi-Fi. And ultimately they settled on Bluetooth for that particular factory, and because Bluetooth worked for them. So don't ask me how.
How does Bluetooth work if Wi-Fi doesn't?
Yeah, it doesn't. So it did not for them in any case. So at the end of the day, it's 2.4 gigahertz. But the point I was trying to make is that at the end of the day, they basically chose all three solutions for their sensor, because each factory that they went to presented some different problem for them. So what we did with the radio adaptation framework essentially was to say that, hey, when you have a device like that, you still need to manage its wireless settings, you need to configure it. And if you keep changing radios, the upper level applications which are managing them, they keep changing too. So from our radio adaptation layer, we just have a northbound API and a south plugin into the drivers. So from that perspective, the user application surface doesn't change. So you usually take whatever we develop here, go to the next one. And that also helps us in, for example, let's even take that there's a Bluetooth from one vendor, Bluetooth from a different vendor. There are some slight differences. So that kind of abstracts those differences out. And then you keep the upper layers the same. And it helps in reducing the overall complexity, especially in the prototyping stage, because you're moving from one to the other. And that's the other part. And then of course you have a host of device management services. I think telecom people are probably more familiar with this. TR069 is one of the standard telecom management object model. But typically, what these device management services do is that they are standards bodies which define certain standard objects for different equipment. The more some of these equipments are very common, like Wi-Fi devices. They pretty much have 90% the same properties, whether the Wi-Fi device is manufactured by Cisco or somebody else. So they come up with these standards and object formats so that it's easy for interoperability. So the people who are actually developing the applications to talk to the devices, they all use this particular common language. And there are of course extensions and customizations based on different scenarios. So we have frameworks built around that area so that whatever common languages are used, we could basically use that on end devices. Then what we have is what we call legacy connectivity, but I don't agree with the name. It's not necessarily legacy connectivity at all. Irrespective of whether it's serial bus or a mod bus or Z-Wave or Bluetooth, it's just connectivity, and different connectivity options have different cases everywhere. For us, the framework is essentially just ensuring that we are able to quickly integrate with different different options out there. And most of the times, like the example that I gave you, we see that within a span of 4 to 6 months, people are changing their communication again. Then we have a few frameworks that help us manage these devices in a heterogeneous environment better. When I say a heterogeneous environment, I'll explain a little bit in the next slide. But some of these frameworks help us do, for example, multi-cloud connectivity. Like the example that I gave you about the street light and the gateway that is managing a street light. Typically, one of the projects that we did was a smart city project where a gateway was mounted on the street light, and it not only controlled the street lights, but it also took data from environmental sensors, and it had a camera attached to it. So now there are 3 different functions. One is street light, one is the surveillance part, and the other is the environmental part. And now all 3 of these data is collected by the gateway, but it actually sent it out to 3 different portals or 3 different applications. One is the environmental agency of the city, one is the police agency of the city, and the other is a lighting agency or utility company, right? So you needed more than just one cloud connectivity. You could not say that, hey, we have Amazon AWS plugin and we are done. So we sort of developed a framework for ourselves so that we could route all of this information across different clouds. So that's the multi-vendor. I'll just pause here and see if there are any questions. Otherwise,
just FYI, Madhu is going to be sending his slides, and when I edit the video, I'll superimpose them. Then you'll have the big screen.
I was misled. So So I prepared this slide to just show where all of these frameworks fit in the overall architecture. So at the endpoints there is application, there's radio and device frameworks, security, network stacks, and then and on the edge part, what we discussed, the multi-cloud connectivity framework, where we are connecting the same application to different clouds. And again, there are two use cases. One is to just route different traffic to different clouds. The other use case is that people switch clouds in between. For the same reason, you use a POC for AWS, when the costs go up, you don't want to use AWS anymore. You want to use some other cloud. So the ability to sort of plug in dynamically and update that framework is what we use the multi-cloud connectivity framework for. We have a concept called home workspaces. Most of the times, I think we're all familiar with logging into our Wi-Fi network and changing the settings on a local web part of it. That is changing. That is changing mostly by making sure that all of that management is done through the cloud applications. You don't no longer log in locally. But in most industrial applications, you do still want that to log in locally. You don't want a cloud application just because of availability of internets or whatever the case may be. Plus, there are other use cases where you want to commission certain parameters locally for troubleshoot some parameters. So we have like a web server built on the edge devices that we customize for different applications. So for example, for building type of applications, we already have something that we know that is commonly used, and then we can build on top of that. Yeah, and I think I'll just leave it at that. I just want to give you some high-level examples and then the frameworks here. So again, just sort of detailing out the multi-connectivity framework. So this is how we do it. So usually the multi-cloud connectivity framework is either running on the gateway or on the fog part of it. So we have our own code sitting here, basically ensuring that whatever is coming from the sensors or the gateway can then be routed to different clouds. So we have an AWS plugin, built in. We have an Azure plugin built in. If it's a private cloud, we'll build a plugin for a different cloud kind of system. This is another framework, again, just as an example of all the frameworks that are there. What we typically see, especially in the telecom cases, is that telecom will have its own PSS, OSS stack, and it has its own protocol. And then what happens is that some of the devices, based on how they have been developed or something, they have different management interfaces. So we built like almost like a translation layer in between, so that we can take just one part of it and then translate it back into multiple, depending on whatever those devices are deployed. Okay. So any questions? So a shout out to Edge Tensor. So one of the things one of our customers is doing is actually doing what Edge Tensor is doing, but on the hardware, meaning they actually have a neural network chip. They call it a NeuroMem 500. Basically, the chip has neurons in it, but it's actually quite simple. It's just basically a memory and a very low compute on it, so that you can map a neural network. And I think one chip has about 1,000 such nodes in it, and then you can also cascade them together to make it a larger neural network. So they built MTS Neural Networks is a company out of Japan. They are our customer, and they've partnered with QuickLogic, I believe, who's making actually the AI chip. And they've developed this camera for smart city applications. This is still in prototype stage. But exactly most of the cases that Edge Tensor does on generic hardware, right? But this is So this is basically specifically for low power devices that are sitting on on the smart city infrastructure. And we are building their entire communication side of things. So we basically, the camera and the AI chip is what their expertise lies. But we are bringing in most of the connectivity part, making sure that the device is operational, upgradable, management.
What's the approximate cost of a device like that?
This is actually pretty cheap. It's in low $100, I think, sub $100, even less than that. The chips are very low powered, and it's not something terribly expensive as far as I know. I can find the exact price for it, but these are meant to be deployed in smart city applications, so they're meant to be deployed in a lot of places, or even like a small surveillance type of systems. So costs are pretty low. I can find out more, the exact rate and I'll back to you. But as far as I understand, that was the reason for choosing this, is to keep the cost very low.
So obviously it's suitable for outdoor applications.
Yes, it is.
What is it? Battery or?
It is battery.
It is battery.
It is battery. Sure.
I'm assuming the neural network is being run in test mode. I mean, it's not being trained in the chip itself.
Yeah.
It's
So
offline training, I would think.
yes. So that's where probably I lack a little bit of understanding. As far as I understand, there is some amount of training that can be done as well. So it's not just the inference mode, and where you actually upload the algorithm again. The way the architecture works, and I can probably get back to you, separately on that, is that there is also a capability of training within itself.
Okay. That training might be just some basic
Could be.
adaptation, because
Yeah.
you cannot train a full-fledged network with the cost point that you're talking about.
So that's something that I am fuzzy about. I'll be honest. But this is something that we are also seeing just right now. And I'll have more information as we sort of develop this into a mature product.
Is this meant, just one more question, is this meant to be a kind of a poor man's version of the deep lens from AWS? Because deep lens has got a deep neural network in the camera itself.
Right.
But the training is offline.
Yes. So again, I'll take that question. I'll think about it. I'll get back to you. So again, they are using the neural chip in a structural health monitoring system. So basically, what this is a battery-powered structural health monitoring system, which is put in buildings, especially in Japan, where there are earthquakes, and they detect vibration. And once they detect vibration, they have to send back a signal alerting whether it's an earthquake or not. Most of the times, the problem was that the trains caused false positives, and you would get a lot of false positives. That's number one. And number two, you wanted the detection at the edge and not have the latency to go back to the cloud and come back with an alarm. So, should I zoom this maybe? Is that better? So if you can see, they're actually attached to the rebar to detect vibrations in concrete. And basically, what they've done is they've sort of trained it to detect false positives better, and then only get the real alarms, and then of course generate the alarm. And now, how do you generate the alarm? There's obviously a communications interface. They used a hybrid system where they have a LoRa as well as a 3G, both of them. The reason why they use that is that they have a LoRa mesh in case one of the towers actually fails. So they, if for example, you have So in a nice case, this sensor camera is working with a 3G connection as well as a LoRa connection. But in a disaster scenario, let's assume that there's an earthquake here and this cell tower gets knocked out, and it has no way of communicating outside. So they form a self-forming mesh and then find out a way out. So that's essentially what we are trying to do for them. We're trying to develop a mesh network and then use our software as a base for all of these devices.
So you created a mesh network based on LoRa radio.
Yes,
it's not LoRa WAN.
It's not LoRa. It's LoRa private.
It's LoRa private.
Yeah,
Okay.
and
You're just using the LoRa track.
Yeah,
LoRa.
yeah, it's not LoRa. Because there's no gateway involved, and we're not doing over a public network. It's like a mesh, private mesh.
Is it your technology? Is the private mesh?
No, it's not our technology. It's the MTS neural networks technology. We are trying to basically help them integrate it with the entire system, basically.
So you're integrating at what point? The hub level or further back?
Both at the device level.
Oh, you are doing it.
Yeah, we are doing it at the device level. And there's no hub here.
Right. Every device.
Every device is a hub.
But where's it? It's sorry. The base.
Eventually, it's LTE.
Yeah.
From any hub, from any device that has access to an LTE.
But it still has to get to that base unit.
Yes, it does. Yes, of course. So if all base units are gone, then yes, we're in trouble. It still has to get out. Okay. So, so this is something that we're doing in the Dallas Houston area. We're developing a connected box for the instrument gauges. This is again a custom project for a particular customer of ours who want their gauges to be connected. That's where Paul is helping us sort of develop this solution from the hardware perspective as well. So, this is like the ruggedized box. So essentially what we're doing is we're converting analog signals, 4 to 20 milliamps that are coming out of digital instruments, and then running an on-premise gateway, which would translate those signals into a dashboard, and then show them on a browser, essentially. So again, this is very specific to a particular solution, but basically these are the type of opportunities that we're seeing, especially in the industrial IoT space.
Quick question.
Yeah.
I know you built this box for this particular project, right? What would it take to do this with off the shelf? If you wanted to go with just off the shelf and not do a custom box, I'm just curious.
Actually, most of the components are off the shelf.
The internal parts are off the shelf. Actually, to do the custom box is actually cheaper than buying a box and trying to grow your own health systems. So the internal parts are basically all
Off the shelf.
So it's a combination of the off the shelf.
Correct. And then putting the solution together, right? I mean, because there are multiple parts of it. The off-the-shelf components, they offer the base case, but to have like a complete solution where it's field serviceable, where you can do updates, you can make sure if things are going wrong. That's where the customization and the solution comes.
So it's mainly a cost.
Yeah, and also this is for the oil and gas industry, so it has to withstand weather and extreme conditions.
Vibrations and
this particular box will measure up to 5 gauges or 4 gauges in a drive stroke count or something like that.
He named it 6-pack box because we had like 6 gauges for this particular customer that we were monitoring. So yeah, that's smart.
Oh yeah, I figured the oil people would like 6-packs.
Sure.
Who's your ultimate buyer of this 6-pack? Is that the
It's
owner
the gauge
operator of the
manufacturer.
well, or is it the service?
Well, we're doing with the OEMs, the gauge manufacturers, or then selling it to the well service companies, to the people at the rigs. So we're actually selling to the gauge manufacturer, and they're selling it to their clients.
So our typical customer base is device manufacturers. We typically don't sell to the end customer because there's a lot of in-house expertise required. For example, we are not experts in oil and gas, we are experts in the technology piece of the connectivity and the IoT part. And you know, the OEMs and ODMs that ask us to do this, they bring the the expertise, the customer service, the commissioning, decommissioning, and we build it to spec for them. Yeah, some of we did some energy management projects. Mostly these were mostly in India. We developed automated HVAC and lighting control. In India, one of the typical problems is that we don't really have like a centralized AC system for small businesses. For larger A-class buildings, they do, but you usually have a split AC in every room. And then each split AC could be of a different brand. So what we did is we used the universal remote on a Modbus interface and then controlled all of them. So some innovative things like that. We developed some sensors for people detection. The typical IR motion sensors would not detect a conference room where people are just sitting and talking and not moving. So we developed an ultra-wideband Doppler thing which detects the radar interference better. So there's some of those use cases there. The other area that we see a lot is smart metering and smart lighting spaces. This is something that we're seeing across the US as well as Asia in terms of developing connectivity solutions for metering and lighting applications. So this is one of our cases where we did a company in Korea, and their customer was the telecoms. That's about it. So, any questions?
For a solution for a customer, are your resources doing all the development? Is it you're doing everything for the client in terms of?
It really depends. So, for example, it mostly again it really depends on the questions. But if you're talking about most of the software, yes, we're doing most of the software. We're doing it on the embedded side on the devices as well. And we also have a lot of expertise on driving the cloud applications for these device management type of applications. So we're pretty much doing end-to-end services. But it also depends on the engagement. Some customers, they bring their own expertise, so we are sort of co-developing with them, and we are sort of an extension of their engineering. So it really depends on each engagement. And in case of the oil and gas box, it's almost a collaboration between 3 or 4 companies. Because we are one of the things that sort of is true in the IoT business is that there's no single player who has all the answers, because it involves a lot of things. So, for example, Paul's company is helping building us a ruggedized box. We have no expertise in it. We are sourcing off-the-shelf electronics. Then we have to work with those companies to sort of do customizations for us, and then we develop the software for the entire solution. So it really depends on a particular engagement. And the more and more we see is that at least that's the nature of the IoT industry. Of course, this probably doesn't apply to companies who have like a very specific vertical solution, and they are completely integrated themselves, right? And they have been doing that. And they're successful. They find a niche market and they do it. But for any other company, at least during the starting stages, it's a collaboration of all of them.
I mean, it seems like you have customers from all over the world, right? So, to the extent that you're able to share this, where do you think is the most traction for your kind of work? Which country or which continent is kind of at the forefront of IIoT?
Yeah. Yeah, so I can give you my personal opinion. You know, at least the way I see it is that there's a lot of buy-in. I wouldn't say a lot of traction, but there's a lot of buy-in from Asia Pacific. They are, and there's I think there is a reason for it. They've been traditionally electronics OEMs and OEMs in that area, so they understand the technology very well, and they are willing to take the risk and adopt it. And whereas in the US, people who do it, they are again, they understand it very well and they do it. But we see a lot of opportunity in industries, in the space of the industry where they're underrepresented. In some sense, for example, oil and gas. You know, we feel it's an underserved market, and you don't have the business imperative to do it just yet, or they're just getting into it. They've heard about it, but they need to get it. But from a broad level vision, not only from a couple of previous experiences as well, I think Asia Pac is more willing to take the lead.
Yeah, for example, in the oil and gas industry, especially a lot of your small, medium-sized companies, they realize they need to do it, but they don't know. They don't have anybody internally that wants to take the lead. Now, a lot of companies are actually going out and hire people to be their IoT expert within their company, and then they're going to decide which of their product line do they want to make smart. Like I got one client, they're actually talking to their customer saying, here's our product line, which one of these do you want to be smart first? Because we realize we need to be in a smart business. What are you looking at? So they're getting a survey from their customers of which product lines they want to make smart first. So
when you approach a potential customer or somebody that you have, before the solution's actually created,
sure.
There's so many technologies obviously that are out there, and a lot of them you're using. What do you tell them at a high level when you say, I'm going to build you a secure solution as well, being that security spans the entire infrastructure?
So if the question is what generally is our approach with the customers for a particular solution, it typically depends on their needs in terms of the technologies that we choose for them. So it's pretty much a very collaborative process in that way, is that we actually understand their technologies. For example, just look at the case studies, right? They're completely all over the map with different technologies and different requirements, essentially. From a security perspective, honestly, a lot of the low-level technologies today are quite security aware. Like, for example, the wireless networks, they are security aware. We have to manage them properly, and then again, security is such a broad topic that it sort of touches at every level. And then security sort of comes into, then you start thinking about authorization. Okay, my asset is out there. Who else is able to access it? Or can somebody replicate my asset? So an asset has to have some kind of an identity, and that needs to be guarded so that when the asset actually comes back to the cloud, it's the asset that you own, not something else that's sitting there. So it's a multi-level problem, and for the lack of a better way to explain it, it's hard for me to sort of say that, hey, this is the exact thing that we do. But security is almost like the primary objective. So if you look at it from a sensor node perspective, most of the wireless networks today do have security already built into the transport layer itself. But there are other problems. You have to somehow manage the identity of the device and somehow authorize it. So there we have again some security frameworks which we can help. Yes.
Tell me a little bit about how Altiux approaches intellectual property in relationship to the stuff you're developing for customers and intellectual property possession to help customers be in a position so they can support themselves in the future.
So there are two ways that I see, at least that's been my experience. Most of the time, a lot of these components are open source, and they have particular licenses in place. And now, some people are averse to that, and some people are okay with that. It really depends on the customer. So sometimes, they would say that, hey, we don't want to use open source. And again, even within open source, there are different variations of it. Some people are averse to GPL, for example, but some people are okay with MIT or open, other type of licenses. So it really depends on their particular needs. From just a disclosure perspective, there are pretty strict guidelines. For example, if you're using a Linux router, you have to have that firmware out in the public space. The source code for the Linux part of it out in the public space, because that's what OSS the Open Source Foundation mandates. So it really depends there. Now we develop some proprietary components. For example, some of our frameworks, we treat them as proprietary. We license them on a license basis, and then they can use it. We offer different licenses. Either it is a binary license where they don't have rights to the source code. If they want source code, they get rights to the source code. That's how it is.
Okay.
I don't know if that answers it.
The only thing that doesn't answer is the stuff of you gluing it all together. How does that intellectual property work? The work
yes.
that you do to glue all that stuff together. Where does that reside?
If it's an off-the-shelf component, for example, it's like any other off-the-shelf component. There is an end-user licensing agreement of the off-the-shelf component. As long as you're not breaking it apart, reverse engineering it, or doing something, it's meant to be used in a solution. Okay. So those cases are straightforward. Now, if you need to do something with an off-the-shelf component, then you need to have some agreement with that provider. So it's then an ecosystem. And it also depends on, and this keeps coming up from a services standpoint. For example, we were trying to talk to a customer who had some particular vision algorithms that they needed to implement. We could not do it. We're not experts in vision algorithm, but there was another company which did vision algorithm. So we sort of collaborated with them to get the technology in place, but then they had the license agreement directly.
Okay.
So that's how
Martha, did you have something?
Madhu, is this based on Ajax by Ajax?
The frameworks?
Yes.
No, it's provided.
All right, if no other questions.
But one thing, I just wanted to add. So we are not wedded to our framework. It's basically the frameworks that we have developed is based on our own experience, and where we can use them, we use them. But we are primarily an engineering services company. So if there is another framework which is competing, which is fine, which is open source, or like HX, for example, we can definitely work with them, because we are pretty much developing the same concepts but at different levels.
Any last questions? Madhu and Mark will be around for a while. Let's give him a hand. Okay?